Test, test, test. There we go. Sorry, guys. Yeah, it wasn't exactly muted. I got upgraded to Windows 11, and it actually was less traumatic than I expected, but a few things went weird. In any case, sorry, I was reading. So first of all, thank you, Befriendle. Sorry, I thanked you, and I guess I was muted. I was also saying he's watching Richard and Andrew's talk, so that's that's the podcast that they recorded recently, I guess. I will say one thing. I think that interview happened a while ago, and some ideas got refined about async. Like nothing terrible, nothing incredible happened in the meantime. But over time, our ability to understand and explain the new async design has improved. So just be aware that whenever you watch something that is a little bit old, you will get in a sense, a degraded experience compared to the new stuff, because we still have some things that we haven't, fully internalized yet, because this is a learning process also while making it. So I don't know, just keep that in mind. Specifically with regards to that interview, it wasn't published a long time ago, but it was recorded. It took a while for the recording to go live, so keep that in mind. Yeah, but it's probably at least 3 months old, I think, or 2 months. I would say at least 2 months old, possible 3 months. Yeah, so I don't know. Keep that in mind. So yeah, congratulations. Thank you. Yeah, I have been updated to Windows 11. Delightful experience. Actually, I'm happy in the sense that I expected it to be worse, while in fact it's, I don't know. I think that the name Windows 11 is kind of a marketing thing. This to me looks like Windows 10 plus a service pack kind of thing, which includes a reskin. That's it. I think we got more groundbreaking updates between, like, back in the days of, I don't know, like Windows XP Service Pack 3 versus Windows XP no service packs. Now with more bloat, yeah. Power Toys is actually pretty cool. Wait, is that one of the things that we can talk? Is it something that we cannot talk about on Twitch? Do I need to turn on the language not appropriate for underage kids? Power Toys. Microsoft Power Toys. Oh my god. It's not installed. Okay, that's a piece of bloat that I will explore another day. Pilot can help you log into your bank. Oh, wow. Anyway, so what are we doing today? Title is Async All the Things. We have a choice in front of us to make. So let me conjure the screen sharing view. And here's the idea. I actually didn't even wrote it completely. So POC IO SCD or IO.thread implementation, or apply async to Ziggy FMT. So these are the two options that we have right now. I guess I'll pull this up. So we're doing async today. No, nothing else. What we do with async changes depending on maybe on what people in chat want to see. So I'm, for once in my life, I'm open to suggestions on what to do for your entertainment. I'm always happy to answer questions and help people understand things, within the limits of what it is that I know how to explain, but I'm always happy to help. That said, usually I choose what I want to do, and you guys only get to watch if you want. But today okay, I'm picking the options, but you can choose. So if you have preferences, so let me explain a little bit better what these two things entail. I'll start with the second one, with Ziggy FMT. So here's what happened. It took me a long time, but I actually, oh God, what did I do? It took me a long time, but I actually have finally, it was finally able to make a good implementation of schema validation for Ziggy. So Ziggy, is my JSON replacement language. These are Ziggy documents. Well, this is one Ziggy document which contains a top-level struct, so the curlies are omitted, but these are different fields in the struct, and then I'm using, like, I'm putting everything on every single field on a single line because it's convenient for the purpose of this test code. But the idea is that it has, structs, it has maps, dictionaries, which correspond to JSON objects. Ziggy is actually a superset of JSON. And then it has the concept of unions. This is a union. This is the case of the union, and this is the payload of the union. And you can see that these unions look like Zig function calls. There's a reason why I wanted the syntax to be different. So I steal a lot of syntax from Zig, but it's not a one-to-one. In any case, I also have a schema language, which ideally is meant to give you a decent schema authoring and consuming experience, both as when it comes to writing and reading other people's schemas. This is the symbol that I use for maps. This is a concept that doesn't exist in Zig. In Zig, you have you have hash maps, but they're not like something native to the language. They're just a user-landing data structure. While in Ziggy, the concept of a map is enshrined in the language because it's a data language. Just like you use square brackets for slices, we do curly, colon, curly for maps. I think that's I like this sigil a lot. So I feel like this has been so far my greatest contribution. Yeah. I want to call it dict. I don't know. Sometimes I still sleep and call it map, but I do want to call it dictionary. Yeah. So So basically, I wanted to implement schema validation, and I've never done this before. So how do you implement schema validation? It's an interesting problem space, actually, because you are iterating two things at once. You are iterating the document itself. That's an AST that you're iterating on. But then as you do that, you also need to iterate schema definition. So, this is your starting point. This symbol here, it kind of means like, what is the root at the top level of the document? What is it? And here we're saying that the top level of the document, it's a full struct instance. So that's why those documents need to be like this. But if you want, you can also say it's a list of those things, or it's a list of dictionaries of those things. What are the restrictions on dict value keys? So there are two answers to this question. Or rather, well, let me answer the easy one. Dictionary keys are always strings. That's why I call them dictionaries. A map technically doesn't have to have strings as keys, but a dictionary does. Like the name dictionary is basically a map that has string keys. So string keys, that's the restriction. As for values, there are no restrictions in the sense that in the data language, you can put whatever you want in as payloads. So for example, here you can see that this is a map that has a key named foo that contains true, another key named foo that contains 10, another key named foo that contains banana. These are three different types, so you can do it. The fact that those three keys have the same name, that's not okay, but that's because this test is testing for duplicate field errors. Duplicate field detection. So, but let's say that you give them, foo1, foo2, foo3, that would be fine. There is a restriction though. In Ziggy schema, you cannot have heterogeneous things this way. Or rather, you have a one bailout keyword. You have any. You can say, for example, you can say that something is a map of any, and then you can put whatever you want as values, and that will match the schema. So the point is, if there is no schema, then you can do whatever you want. You can basically use this thing in the same way that you would use JSON. And so you can make all kinds of weird soups. But if you use the schema language, then either you bail out completely from type checking. So you say that's a map of a dictionary, goddammit, a dictionary of anything. Or if you want to say that this is a dictionary of something, that something has to be homogeneous. So a properly typed dictionary or a properly typed array will have all fields of the same type, period. So that's how it works, unless you do any. But the idea is that if you're making some, the idea is that if you're making some kind of config file or API data format, like some kind of data exchange format that is being consumed somehow, be it a config file, be it a data file, be it communication over the network, they can have a union value. So yeah, you can do a union and then each tag is a different thing. So totally you can do it that way. But the point is, if you're doing if you're making a schema for those purposes of inter-exchange with other people, you're encouraged to make it nice and not insane. So for example, the idea that, this config value wants it to be a list of a Boolean, a number, and a string. Like, what the heck? It's insane. And you can specify that with JSON schema, which I think it's actually a bad feature. The fact that you can, it's a bad feature. So I guess similarly, the fact that you can't in here, I think is a good thing. Yushman. So, okay, so this is the state of things. I finally implemented this thing. As I was saying, you have two trees, right, that you have to navigate. And so as you navigate this guy, you need to navigate this guy, but then you sometimes have to jump because some things are by name. So whenever you see another struct or a struct or a union definition, you have to jump. So you have to resolve this name. And so there's also scoping rules that you need to follow. And then there's any, because here's the thing, in all other cases, whenever you are navigating into a value in the Ziggy document, you're also progressing to the corresponding type in the schema. Although, to be fair, almost, because here a dictionary, for example, means that whenever you enter this dictionary, you have to do this, you navigate to any once, but then you also have to return back to the dictionary to process the second field, because you need to process this rule against all these fields. So there are, like, how can I say, you need to keep them in sync, but it's not linear, right? You need sometimes to have this thing jump back and then they continue, and then this jumps back again and then they continue. And any is also weird because any, for example, here, bar is any. And in this case, any is a list of a variety of types, including a struct and a dictionary. So when you encounter any, you cannot progress on the schema side, and as long as you keep going deeper into the current value. So you need to consume the full value, keep validating it, because this is the step where we validate duplicate keys in dictionaries and structs. And then once you pop out of this element, it's only now that you are able to go back to return from the any. So there's a bunch of things that you need to keep in mind. This was very interesting, but I got it right. So I'm finally, I haven't fuzzed it yet, so there might be other errors, but I'm finally in a position where I'm happy with this thing. And this is what I did. Okay. I'm happy with this thing. So I'm finally able to explain this. So I'm at a point where I need to start looking at the CLI tools. So FMT, is the auto format, is the sub command that you give to the Ziggy CLI tool to format stuff. And one way of using it is, I'll look at the help menu, is that you can launch it and try to get the input from standard input. That's fine. You can launch it on a single file. That also works and it's fine. But you can also launch it on a directory. And if you launch it on a directory, then what happens is that it will it will run recursively on the path, on the directory, looking inside of every subdirectory, searching for Ziggy and Ziggy schema files, and try to format them. So this seems something that could potentially benefit from async, right? Because right now we do it in a 100% single-threaded mode. Like we call format file, we try to open a path because we don't know if it's a file or a directory. And looking at the extension, like if it's, you know, .ziggy, then it's a file. You don't know that. That could very well be a directory that has .ziggy in the name at the very end. Could totally be. And also ZGY. No, I removed that. I think I'm backing off from the alternative file extensions. So that's why I've removed their mention from here. That was an old idea that I don't think I want to maintain. Sorry. I think I'm going full in on the Ziggy extension, file extension. In any case, so you know, you enter format there, and then it keeps going inside of itself, trying to find files. And that's it. And this is a dir. Oh, this is a dir walker also. Okay, so format dir is the entry point, and then we do a dir walker. So in that way, we do format file. So what is my point? My point is, wouldn't it be nice if here we could say, well, let's try to run this format file call on a different thread if it's available. If there isn't any, you know, you built in single threaded mode, or you know, you only have one CPU, meaning that, you know, we could do threads but wouldn't make any difference. Then we don't. But if they are available, then why not? Why not do that? So this is one thing that we can do. This shouldn't take long. It requires just making sure that, you know, I mentioned this in Germany. Pretty much the only work that you have to do to make format file work is the same work that you would have to do to make format file work in a multi-threaded situation. That's pretty much it. That's the only thing that you need to work around, and then you just plug in async and you're good. Alternatively, POC IO thread implementation. Oh, somebody mentioned one vote for Bork. That is a more serious project, but I think it's possible. I'm going to put it here. Yeah. Bork could totally deserve being ported to async. So let's do it like this. Okay, so we could async Bork as well, which is this bad boy here, which also has a bug in the YouTube integration. Never figure out why. Looking forward to see, hopefully, that problematic behavior disappear on its own when we upgrade implementation, or when we upgrade Zig. Hopefully. I mean, eventually I'll have to do it because it's either that or we don't maintain Bork anymore. Then here's the one here at the top of the list, POC IO threaded implementation. So here's the story. This was a discussion in Zulip. So I'll give you the short version. I'm not going to give, I'll not do a journalistic recount of the whole story because I would have to read everybody's message. I won't. But basically, Andrew was implementing So Andrew implemented a thread pool implementation of IO, and he demoed it in Germany. The last example that he made on paper was not supposed to deadlock, but it did deadlock. And my conclusion at the time was this should not deadlock, but we weren't 100% sure. Then they had some discussions where before I could read, because I think they all returned from Germany faster than me. So they had this discussion where they're saying, wait, this deadlocks, this should not deadlock. And so some discussion was about, wait, maybe is it that maybe we need some more semantics, some more primitives? Like, did we mess up some of the semantics? Then I joined the discussion and a bunch of exchanges. I'm not going to read everything because the interesting part is later on. But the point is that basically my opinion was this was something with this implementation, because normally all other implementations would be fine with maybe I should bring up the exact example. It was one of these things where basically you have a queue, you have a producer, and then you have a consumer. And the idea is, if you do IO concurrent on both, it works. But if you do IO concurrent on the first and IO.async on the second, it deadlocks. And again, based on my theory of how async should work, our implementation of async should work, this should be fine. You should be allowed to have the producer be concurrent and the consumer be async. That should be fine. Because what happens is that if you make the consumer async, then assuming that you start the producer first and then the consumer second, if you make this async, so if you make it concurrent, it works because you spin off two new threads, and they just do it. If you use async, what happens is that either you spin a new thread, which works, or you don't, and you quote unquote consume the current thread. Like, you use the current thread that is currently executing this main function, and you use it to run this function. And that is also fine, because this works as long as, how can I say, like, because this guy is already running on a separate thread, and you know that that's the case because IO concurrent guarantees that. So so that's why, in my opinion, it was supposed to work. But what was the problem? The problem was that Andrew's implementation was basically adding a job to a queue of jobs, like a task to a queue of tasks. Every time you have a link to the discussion. Is this available publicly? Yeah, it is, because I'm not logged in. There you go. So what was I saying? So his implementation was basically doing this. Every time he would see IO.async, it would queue up, it would put the task on a queue. And so if you had enough threads in the background that would pick up that task, then you would never deadlock. But once you started doing this threaded CPU count equals 1, then there's only one thread which is currently running this function. And so there is nobody else to pick up that job from that queue. So the job would remain queued forever. And in his opinion, that would have been a legitimate design, while in my opinion, that design was flawed. But to be fair, the reason why Andrew was hoping that design would work is because that was a design that was based on work stealing, and it was based on what actually can work with green threads. Because with green threads, this all works without any problem. Because with green threads, whenever a task blocks for whatever reason, it blocks because it's waiting on the network, because it's sleeping, because it's trying to read a file or write a file, or it's trying to pop from a queue. Every time it's trying to do any of these things, the task is suspended, it yields. And so the thread becomes free to go and do something else. The problem, though, with thread pool is that thread pool doesn't work that way. The thread, this one, threaded implementation, instead doesn't have any form of green threads, doesn't have any unit of concurrency that you can detach from threads. It just has threads. So that also do blocking IO. So whenever a thread is busy doing something, it stops there. So whenever this thread stops awaiting for this thing to be completed, it blocks there. It never yields. So the thread is consumed blocking on that task, while in any other async implementation that we're going to have, what the thread will do is instead detach the unit of concurrency, detach the green thread, detach the stackless coroutine, and by detach I mean somehow save the state somewhere and then jump into executing something else. But it can't in this case. So that is the core of the problem. So in the other models, you can queue up tasks and it works, but in this one, you just cannot queue up tasks. So, so a bit of back and forth, where my conclusion is that there we go. The conclusion of the day was, I think there's a lot of confusion in the discussion because people in the meantime were talking about other primitives like io.eager, which is something we don't have and we should not have. io.yield? No io.yield. Bad. First of all, it doesn't work. Like, you just cannot implement io.yield. In the IO threaded implementation, you just cannot implement io.yield. It doesn't exist as a concept. So, so there was this discussion, but I was not convinced. And so I said, I think there's a lot of confusion in the discussion, including on my part. I'll take some time to digest and think through everything through. So we left it for the day. And then after a while, the day after, I came back with a super minimalistic example that we could all trivially agree that should not break, that was actually breaking with this implementation. Let's see what's happening here. Ziggy newbie here. When having a multi-threaded environment, does that mean there is no need for an event loop like implemented in libuv using Node.js? I'm not sure how to answer your question directly. I'll answer a slightly more general version of your question. In Zig, you can spin up new threads without an event loop. You can create a thread pool. You can just do std process.spawn and wait, is it std process spawn? Std process thread spawn? I don't remember. In any case, you can spawn threads and manage them, directly that way. But the new version of Zig has async await in it. And async await is basically a way of, it's an abstraction built on top of all of that. So you can have basically an event loop that runs all these things for you, so that automatically dispatches work on multiple threads if they're present, or you can even have an event loop that runs on a single thread. That is also variable, because if you're doing non-blocking IO and you have either green threads or stackless coroutines, then a single thread can still pause one thing and jump into doing something else. And the pausing of the thing they was doing before can happen every time there is to wait for a socket to become readable or writable, sleep, waiting for a lock to be released, that kind of stuff. So the point is, multi-threadedness and an event loop are things that interact, but they are in a sense, still relatively perpendicular. Not entirely, because they do interact, but so you can have an event loop or not. You can have multi-threading or not. You can have an event loop with multi-threading. You can have multi-threading without an event loop. You can have, you can have all of it. So these IO implementations, some of them are event loops. I would say IO.threaded is the closest to not being an event loop. Is there a way to fire and forget a task? Right now, I'm using a group and the futures are completing almost immediately, but the memory for each future stays around until I wait the group. There is no way to fire and forget an async task. My understanding is that, oh, I see, because group is still allocating memory for all the individual futures. I'm thinking that this is an implementation problem. So I don't know how the current group is implemented. I remember seeing a few different designs, and Andrew and Matlag discussing, design A versus design B. I think that one of their designs was based on the idea that futures would be released meaning that when you put something in a group, that thing, like, you don't pay the cost of keeping futures allocated around. You only pay the memory cost of keeping the group around. So I don't know if the current implementation has the property or not. The way you're talking seems that it does not. But it seems that then a different trade-off could be made to have, a different implementation that maybe doesn't have this problem. That said, no, the answer is there a way to fire and forget an async task? No, the group is the way you do that. You cannot fire. It's a bad. It's a broken idea. Fire and forget, like full blown fire and forget. Think of Go, for example. Just doing Go of a function without any form of control over it. It's a dumb idea. Like, because the instant you need to make your software even remotely polished, you want a clean shutdown. You just want a clean shutdown. You can't have it anymore because you did fire and forget, or then you can, but to do it you need to wire in back in some form of control, right? Some kind of thing that the thing can observe. So at the end of the day, we want the wait group to be the abstraction for fire and forget. If the current implementation has some things that are missing, then I guess it's a matter of understanding if there's a way of tweaking that. And if there is no way of tweaking that, then I don't know. Sorry, no, never mind. Regardless, whatever happens, wait group is the way. Soon to become Zig newbie. Okay. I'm coming from C, but I was debating Zig versus Rust. How's the transition from C to Zig? Go to zigland.org, read the language reference. It's a single page document. It will take you probably between half an hour and 1 hour to scroll through it, reading, most of it, not all of it necessarily in maximum detail, but like just to get an idea of the language. And if you know C, then most of the concepts will make sense to you, and you will have a decent overview, in my opinion. Bare threads can fire and forget. Yeah, that's true. You can fire and forget with bare threads, but man, that is a problematic thing, man. People use that to do not good things. I don't know. I feel like it's I would be delighted to be proven wrong, though. I would be delighted to see a use case be presented that is, not too terribly convoluted, where there is a clear value proposition to have, pure fire and forget. My suspicion at the moment is that there really is no such thing. I believe that there is no one singular use case where that will be the case. I think that in all cases, having a wait group is better. That said, I will agree that if you need to keep around the memory for futures, and you could avoid having to keep around the memory for futures if you were to do fire and forget, which by the way, it's not guaranteed by the current design. It depends on the design. So it might be that the current design really needs futures. I'm not sure. I don't think that's the case, but I'm not up to speed with the latest and greatest implementation details. And also there's multiple implementations. So unless it turns out that doing pure fire and forget is the only way to get rid of futures, then yeah, maybe you have an argument. But otherwise, just do group.async. Okay, back to the main discussion. So after sleeping on it, I came back the next day with this example, which is a trivialized version of what we were already looking at, but so trivial that we can all agree this has to work. It just cannot block. So what was happening here? We start a threaded implementation. We put CPU count to 1. We try to call save file as an async task, which will, just save the file and sleep for a second to simulate doing some work. So it's not even really doing any IO. And then we await for it to complete, and then that's the end of the test. Well, this currently, with the current implementation of IO.threaded, it deadlocks. Why? It deadlocks because this call to IO.async puts a task, like creates an entry, puts on a task queue the fact that we need to run save file with these arguments, and then it goes here and it blocks, waiting for this future to be fulfilled. What is the problem though? Because the CPU count is 1, we only have one thread, this thread, and now this thread is here stuck, waiting for something that nobody else will ever do. So this deadlocks. Should this deadlock? The answer is obviously no. This should not deadlock, because if you give these semantics to async, and this is where the discussion for async versus eager or whatever else was happening in my absence. I will say in my absence. I'm the gatekeeper of of the async theory. I don't know why. It just I feel like this just clicked very well for me. So I also sometimes get confused by this stuff, but for now I tend to have a decent handle on the like big picture. So I think it's obvious that this should not deadlock, because this means that async should be your main primitive for expressing that things could be done at the same time if possible. And so if it doesn't work when you just have one threaded equals 1 and it deadlocks, it's such a broken primitive like this. So you could create another one to express some different combination of properties, but man, async like this would be terribly broken. So with this example, I said, well, I'll read what I wrote. This locks, and I think we can all trivially agree that this should not be the case. Now that this is the same problem, this same problem persists as long as there is a limit to the number of running threads, because this is the version where we're only saving one file. Actually, you could even argue that from a use case perspective, this is a silly use case. Like, you wouldn't write it this way if you were only writing one file. But if you expand it a little bit and you say, now I'm going to try to save 2 files at the same time, now it makes more sense. And the problem is that the moment that the number of async tasks that you want to schedule matches the number of available threads that you allow in the pool, then the moment that happens, you will encounter a deadlock with the queuing strategy. So thread pool must have as many threads as there ever are as yet unawaited concurrent tasks, correct? This implementation, yes. Yeah, this is exactly what I was trying to explain right now. Yes. This design has this problem. The problem that there always has to be a free thread for this design to work. And that's a problem because you will encounter a limit, and once you hit that limit, you will deadlock. But here's the funny thing. The funny thing is that even though you have this problem, if you think about it, it's funny because you wouldn't have this problem if instead of queuing, you just run the function directly. And this actually shows an interesting quirk of the current implementation. I think I have this on my computer, so I can even, actually maybe I have it already written down, or I have this other version in here. Okay, let's go back to this implementation. Let me demo everything. So here I have, oh shit, I wrote it on Rustlock. I should not have done that. So this is Rustlock. Okay, I'm gonna call it sync.zig. Oops. Okay, there we go. So let's watch the Deadlock. Test never completes. We're stuck in there. Let's watch it succeed. Saves A and it works. Why did it work? Because it removed this limitation. With this limitation, having threaded CPU count be equal to 1, that's the problem. So I have, what is it, 16 threads? I don't know, but you know, if once I comment this out, if I were to change this to, if I comment this out, sorry, which means that this value will be set to the number of processors that my system has. Oh, sorry, ZLS doesn't allow me to go to definition because I have ZLS built for a different version of Zig, so never mind. But if I were to look at it, it would basically default to nproc, so 12. So this would default to 12, and so I create here 12 async tasks, and well, depending on some performance issues, we could still deadlock. So, but here's the funny thing. Okay, here's the funny thing. If I run this with -f single threaded, then it works. And it works even if I leave this on. Why? Because in this implementation, Andrew correctly special cased the fact that when we are in single threaded mode, every time you try to call something with IO.async, it must be run immediately. So we can look at the implementation, I think, of this IO.threaded function async. There we go. If it's single threaded, run it immediately. So, and otherwise, async closure of blah, 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 and otherwise it adds it to a queue. The problem is that, so I guess my point is that it's kind of funny because he does the right thing when this implementation does the right thing when in single threaded mode. And, but if you think about it, single threaded mode and CPU count equals 1 are conceptually the same thing. Well, at least when it comes to async. To be more precise, the reason why these two things exist and they're separate is, well, I mean, well, first of all, because you could put a different number in CPU count, obviously, but also because IO.concurrent has different semantics. IO.concurrent will always spawn a new thread no matter what. But in single threaded mode, IO.concurrent will always fail because in single threaded mode, you're just not allowed to spawn new threads. So this is where the different stands between this and F single threaded mode. But if CPU count equals 1, always run the function, the code immediately, just like F single threaded does, then we would not have any deadlock. And okay, to move forward with the story, this is wrong. This should not be like this. Obviously, this should not deadlock. So here's my point here. IO.threaded cannot queue work. It needs to have a linked list of available threads, or, sorry, maybe I should have been less precise. The point is, it needs to have somehow knowledge whether there is another free thread or not. If there is a free thread, then, or spin up a new thread if, we haven't yet spun up all the threads that we know we are allowed to spawn. Because this is, okay, small parenthesis, because I think this might be useful. It's a thing that Andrew did that I think is a good idea, where when you spawn a program that uses a threaded IO implementation, it doesn't immediately spawn all 12 threads. It only spawns them. It only spawns them if there's a need for them. And I think that that's a good choice, because you want to be able to say, yes, this is we're doing a thread pool IO strategy, but maybe somebody is just calling the help subcommand, and so there's no point in spawning 12 threads if you're never going to use them. So they only get spawned when needed. So that's why we are like always specifying that the idea is there's going to be a limit of threads, of how many threads you want to have in your thread pool, one way or another. So the idea is, if you either find a free thread that was already spawned that is there doing nothing, or you can spawn a new one because we have yet to hit the nproc number, assuming that we want to use that as the CPU count value, which is a reasonable default, I guess. Then awesome, and you take the task and you schedule it on that thread. But if that fails, in the absence of a free thread, the task must run immediately. And that is the key difference, because this current implementation here doesn't do that. It just queues everything on a queue, and then it might be that all the other 12 threads, 11 threads, are stuck waiting for something, and they will never unstuck because they are not able to yield. They have to block, waiting for the condition to continue their execution to be fulfilled. This is specific to IO.threaded. I'll repeat this one last time. IO.threaded has to work like this because it's purposely using threads without green threads, without stackless coroutines, and it's also doing blocking IO on top of everything. So this is the implementation that has these quirks that we need to work around. That's it. So Andrew replied saying, basically, I think from Andrew's perspective, he was hoping that he could have some kind of work stealing schema work in implementation. But the problem is that there's this tension, right? Because you can't queue, you cannot queue tasks hoping for a thread, for a currently busy thread to become free, because that is not guaranteed at all. It is guaranteed with green threads, because with green threads, when a thread hits a sleep, hits an IO operation, hits a lock, it doesn't actually stop there. It saves the state. I'm gonna use green threads as the examples. It's gonna save the state of the CPU in memory, in main memory, and leave that thing waiting there and jump into something else. So something always makes progress if it can. But with threads, that's not what happens. With threads, if there's a sleep, the freaking thread sleeps, it's gone until that sleep is completed. So, there's ways of waking the thread up early, but the point is that the thread will have to perform the blocking operation. It cannot yield. That, like, the primitive that allows you to turn a blocking operation into doing something else is yielding, and we cannot yield with IO.threaded. So so in any case, I think that we all agreed that this property that tasks won't be queued up and get stuck forever is a property that we must guarantee with IO.async, because otherwise this breaks, and that means that IO.async is pretty much worthless. And it doesn't have to be, because, as we were saying, it's so easy we just need to be more strategical when to run the function immediately. And that's it. So, okay, this long explanation to say that that the IO.thread implementation has to change no matter what. Andrew, I think, is going to be away for a couple of weeks. He's been busy with other stuff, so he's not going to work on it for a while. He's also going to Japan. He will be present here. He will be at the first Zig Day Osaka. Oh, which was not announced yet. I need to talk with the organizer. This is going to be November 15th. The organizer hasn't announced it yet, and yeah, I think I need to nudge him a little bit. So, in any case, so this is how I imagine this thing should work. So, so this is how I think, and this is a design that assumes that you just cannot or at the end of the day don't want. It's not optimal to do any work stealing system. Like you just structure it differently. So the idea is, instead of having just CPU count, we have two separate variables: concurrency limit and pool size. IO.async is allowed to spin up new threads up to pool size. If a call to IO.async is unable to find an idle thread, and we've already hit pool size, so we cannot spawn new threads for IO.async, then we run the task immediately. Keep in mind, this whole concept of knowing that there is an idle thread is missing from the current implementation. The current implementation has no knowledge whatsoever if another idle thread exists or not. There's only the concept of a queue of tasks. So IO.concurrent instead is allowed to oversubscribe the number of active threads past pool size. So IO.concurrent also can add new threads, and as long as it's adding new threads below the pool size threshold, those threads remain running up to concurrency limit. And if concurrency limit is hit, then IO.concurrent returns an error. So this is the total concurrency limit is basically the total maximum number of available threads that the process can spawn. So it is guaranteed to never go over, at least while using the IO implement. At least when it comes to the IO implementation. Obviously, if the user code explicitly spawns another thread, then that will bypass this limit. But that puts a hard limit on the number of total threads. Once the task is done running, if the thread was an oversubscribed one, it gets shut down. In practice, here's how I envision this. Oh, sorry, I'll read the last sentence and then I'll explain more. By default, concurrency limit could be set to 0, so no limit. We assume that 0 means there is no limit. And pool size, we set it to nproc. This might already be answered, but could you always make async calls eager? This approach basically seems like async is sometimes eager depending on if there is a free thread. So if by eager you mean that the current thread runs the function immediately instead of scheduling it on another thread, yes, you could make it always eager, but then IO.async becomes worthless because it's just a function call. That's what you would have normally, given this definition of eager. The idea of async is basically this. If there is another thread Well, it's not strictly another thread. We're talking about threads with IO.threaded. In the case of green threads or stackless coroutines, the point is not exactly whether there's another free thread or not. But in this case, in IO.threaded, which doesn't do green threads, doesn't do stackless coroutines, it just does normal operating system threads plus blocking IO. In this context, then yes, whether there is another free thread does make a difference, but that's kind of the point, right? The point is that you want IO.async to mean if we have resources, which in this case is threads, in other implementations could be something else, but if there are free resources to do more stuff at the same time, please do. If there aren't, then it's also fine to do this stuff sequentially. So I think the quintessential example for this, in my opinion, is this one. I think this is the quintessential example. Here you have a function that calls save file twice. First we save file A, then we save file B, and then we tell everybody success. But with async, you can do this. You can say, look, we need to save file A, we need to save file B, but here's the idea. Those two things don't have to happen in order. They can happen in any order. You could save file A, you could save A first, you could save B second. The opposite, you start with save B and then file B, and then you do file A. You do a little bit of A. Imagine that the files are big. You do a little bit of A, then you do a little bit of B, then you do a little bit of A. That's also fine. So when that is the case, that's when you use IO.async. And so what IO.async should give you in return, and look, you're adding a bunch of syntax that you didn't have to put here, right? So what IO.async gives you in exchange for the extra syntax that you have to put around it is that when the resources are available, those things will happen in parallel, hopefully, and thus they will take less time. That's your ultimate goal here, basically. Your ultimate goal is to get access to parallelism when it's available, and when it's not available, then you still want to say, well, that's fine too, which is different from another primitive, which is presented. Holy shit, it's presented nowhere. Oh, sorry, it's presented only at the very end in this blog post. There's another different situation where you have, I'm going to use a different example than this one because I discovered that this confused the heck out of people because nobody knows how TCP sockets work, especially listening sockets work. So let's use a different example. This is different than when you have, for example, instead of doing save file A and save file B, you have, for example, function A, and function A needs to observe some, for example, it wants to access a lock that it's currently closed, and then it's going to be only function B that will open it. And when function B opens it, then function 8 can conclude. So function 8 does some stuff, then waits for a lock, which is currently locked, and you need to have scheduled and made progress in function B as well, because function B is the one that will maybe do some work and then unlock that lock, and only then this guy can proceed. So when you have a situation like this, which can happen, then you need what we were calling here async concurrent, which we actually renamed this to concurrent. I should change this blog post, I guess. We renamed this to just concurrent. So the idea is you can communicate to the system where actually those things need to happen concurrently. You cannot serialize them, because if you serialize them, then they will deadlock. The example that I was using here is a server and a client trying to connect to one another. So like instead of doing async save file A, async save file B, you do you want to start a web server, and then you want to connect the web server as a client, and the server, imagine that it's a test. The server needs to process the client successfully for the test to conclude. And so If you use async, then you're communicating that it's actually fine to do these things sequentially, but it's a problem because you start the server and you block there, and then the client never comes into existence, and so your test will deadlock. So that's why concurrent is a different primitive than async. So where I was going with this? Well, I don't know. I hope that this explains the point. So long story short, no, you don't want to have async be always eager. You want async to be eager as a fallback. Ideally, like from optimistically, you would want async to always be able to schedule tasks on another thread, because you know that means better performance, roughly speaking. But then at some point you will run out of threads for one reason or another, and so to make sure that your stuff doesn't deadlock, it needs to run the stuff eagerly. But then if IO.async always runs the stuff eagerly, then I don't know, it sucks. That's it. Oh, you know what? Maybe I misunderstood your suggestion. Maybe your point is what if in IO.threaded only IO.async run stuff eagerly? If that was your point, sorry, maybe that is the interpretation that I should have gone with. So if your point is, well, other implementations can do whatever they want. They can do the optimal thing with IO.async. But IO.threaded, since it's problematic, that one could always run these things sequentially. Yes, you could do it, and that would work. But then IO.threaded would be, in my opinion, suboptimal, in the sense that a version of IO.threaded that tries to schedule stuff on other threads would outperform the always eager implementation. And I think we can have it. So we should try to have it. And so here's how, in my opinion, this should work. I think that there should be a thread pool. So if we start a thread pool, and I think that we should have a way of querying the thread pool to know which threads are free, or if there is no built-in way of doing that in the thread pool, then we should shim it in ourselves. Like we should basically have some kind of atomic variable that we increment, decrement, that we can look at to know if there is currently a thread that is doing nothing. And so that way we know if we can give a task to the thread pool and the thread pool will execute it or not. Actually, the thread pool might even have an interface that allows doing that. Reading the thread pool sounds like a race condition. There has to be a way, though. I mean, sure, you need to do that in a smart way. There should be like an atomic system, like an you know. Here's the idea. Worst case, you just lock the freaking thing. Just lock it. Snoop around and then unlock it. I don't know. But that's what you have to do to make this work, in my opinion, because the pure queue is just, it's maybe potentially more performant, probably more performant, but it's broken. It's just semantically broken. So in any case, the discussion then proceeded with other stuff. There's a regression on Windows, apparently. So package fetching on Windows is broken. And apparently there are some bugs in io.q, but that's a different story. We don't care about that for now. So one idea could be, let's try to implement io.threaded this way, which means take the current implementation of io.threaded and tweak it to work this way and see how far we can get. So these are the options. Let's see, what time is it? 5:30, 5:40. So I'm not going to say forever, but I already ate dinner, so I can say for a while. And we can do any of these things. So anybody in chat have any strong opinions on what to do first? If I don't hear strong opinions, I will probably start with asyncing Ziggy FMT. Hopefully shouldn't take long. And then move into the first one. Make a cup of coffee. No, man. I need to take it easy with caffeine. It's already 5 p.m. Yesterday I already had not the greatest night of sleep because I abused caffeine a little bit too much. So yeah. Classic ring buffer bug of not differentiating between empty and full queue. Was there already a fix merged or PR'd, or is it still waiting? POC threaded then bork. Okay. X2, you want me to do the serious stuff. Okay. By the way, no promises that I will make a ton of progress on the IO.threaded implementation. We'll see. It depends on how weird it is. Because there might be a bunch of weird stuff that I might take a bit to get used to. I mean, I understand the higher level schema. I have not read yet end user implementation. That said, it shouldn't be too terrible. Okay, everybody wants to do the POC. Let's do the POC then. So, okay, what's our goal? Our goal is these deadlocks. What if it didn't deadlock anymore, right? Currently deadlocking, but what if it did not? I should probably look at my Zig setup and to make sure that it allows me to do all the stuff that I want to do. So let me think about it for a second. IO threaded is in the standard library, so I don't even need to rebuild my compiler. So I think we can do this. Okay, this is where I have my master merged 7 hours ago. Oh, nice. I should probably update my stuff, shouldn't I? Okay. Did everything break horribly? Should I rebuild my compiler? I should probably rebuild my compiler. Kangaroo 12. What the heck is going on with cartography? Why is everything named so weird? Like watch me add in the standard library a file called kangaroo12.zig. See how long that file lasts anywhere else other than inside SDD crypto. Just saying. Anyway, build. Okay, let's just do one round of rebuilding the Zig compiler since I pulled stuff and we don't want to start getting weird crashes that it turns out it's not even our fault. So so here I have this directory. That said, we don't have to wait for that to happen, or rather to complete before we can take a look at source code. So this is IO threaded. I'm gonna zoom out a little bit. Baboon balloon. God damn it, man. Okay, so let's see. Oh, there's also cancellation, right? So here's one part of IO threaded which is absolutely non-trivial. Cancellation is messed up, but that's, I think, fortunately something that we don't have to touch either way. The reason why cancellation is messed up is because I did mention that IO threaded is using blocking syscalls, right? So how do you unblock a thread from a blocking syscall? POC threaded is attempting to prevent deadlocks on async using finite threads. No. POC threaded is attempting to is fully solving the deadlocks using a design that is not based on having a queue of tasks somewhere that threads pull from. So basically, you see this, right? This run queue. The idea is to get rid of the run queue and either replace it with free threads. So having a linked list of free threads, or having a thread pool. I don't know yet what the approach should be, but the idea is to certainly to nuke this field. Also, oh, you know what? I'll show one last thing though. Well, since it's, oh no, wait, oh no, oh yes, it succeeded. Okay, I thought it failed. Let me see if I can show you one last thing. Um, I don't remember. Did I show this? No, I think I did not. Oh, actually, I have a few things to show. Okay, so first of all, this was it's a piece of art that was created by the organizer of Zig Day Osaka, which is very cute. And it's interesting because this is not even the full banner. This is not the event banner. The event banner, you saw it early. It was cool. But this is just a piece of art that was made. So nice. But okay, check this one out. So check this one out. This is Mason. This is a skate park in my town, and this is Mason skating in the bowl. And I have one also of Andrew. Well, I have more than one, but I'm not gonna show. I'm not gonna show all of them. Oh, you know what? Have another Mason. This one is also cool. And I'll give you one Andrew, and then this is gonna be it. See, what do I have from Andrew? Oh, I have this one. So now you might be wondering, did he land the trick or not? So he was coming up from the bowl, the pit. I don't know what they call this thing. From the hole. So he was coming up from the hole, and his goal was to do, I think it's called a 50-50, the thing where you basically put your skate on the metal bar, one wheel to the right side, well, two wheels to the right side, two wheels to the left side, although one front wheel on the left side, one front wheel on the right side, same with the back one. And the question is, did he land the trick or not? Maybe he did, maybe he didn't. You don't know. You can't know. So you should just assume that he did, I guess. Anyway. So I just wanted to show these pictures because I think I didn't show them. I think it was nice. Need to track when threads finish in order to decide whether async runs in a thread or on main. I guess we should see what thread pool has to offer, right? My idea is either thread pool has some feature to offer that allow us to know if at any given point in time there's a available thread for us to use, and also a way of making sure that there is no race around that, right? Because if it's just, let's say that we do it in the super naive way, there's like a variable in the thread pool that says how many free threads are at any given point in time. Obviously, just reading that value is problematic because two different threads could read the same value. They both think they can schedule a task on a free thread. Turns out that there's only one thread. One of the two tasks run, the other one gets queued up, which is how you get deadlocks. So would it not make more sense to run the code at the await point? Oof. Sometimes maybe. That also comes with a big set of trade-offs. That comes with a very big set of trade-offs. None of the current implementations runs the function at the await point. I think it's a more counterintuitive design because I think it's easier to reason about what your stuff is doing if you think about the code running at the async point, not at the await point. But I do think there are some. I remember we talked about this option at some point, and I think there were some positive things with doing this at the await. That said, here's one, for example. If you want to start something and then you have a 50-50 chance, statistically speaking, that you will cancel a task or await it, then obviously by running it at the await point, you don't pay the cost of running the thing at all 50% of the time when you're going to cancel it. That said, it's kind of an artificial example because, the programmer, could delay calling the thing, doing the async call. You could store that data somewhere. So in any case, currently none of the things that we're implementing does that. It's not completely off the table. But at the moment, it doesn't seem something that we're going to do anytime soon or at all. Because based on discussions that we had, that I've at least participated to, it didn't seem a thing that would bring a lot of advantages. Can thread tasks spawn other thread tasks? What do you mean by thread tasks? So your primitives are async, concurrent. So X2, are you saying, can a function called via async call io.async in turn? Yes. Can a function call via io.async call io.concurrent inside of it, like in turn? Yes. Also vice versa. Will it also make the single thread version deadlock? I don't think it would have overall a big difference with the current problems that we have. Concurrent uses the same IO parent to call IO concurrent again. Yeah, that can totally happen. Absolutely. What happens if a parent is cancelled? So I guess it depends on the implementation. But generally speaking, what happens is that the parent being cancelled will make so the parent being cancelled will make the parent. The assumption is that the parent is stuck on something. So if the parent is computing, let's say that you call via IO concurrent something that doesn't do any IO, like it just computes Fibonacci and then returns the value. If you try to cancel that thing, nothing happens because that thing doesn't have any suspension point, and so it just computes and then returns. But let's imagine that instead the parent calls other concurrent stuff and awaits them. Not guaranteed, because it could call concurrent and then return them, add them to a wait group that it does not await itself. So there's a variety of schemes that you can have. But let's say that the parent calls IO concurrent and then awaits the children. So it's awaiting. When you cancel the parent, what I believe happens. So let's say that instead of awaiting, it's the parent is reading from the network, because with the specific of awaiting, I'm not 100% sure. But if it's like reading on the network, the parent will, the call to read will return error.cancelled. So the parent now is unblocking itself from a network operation or a sleep. It's unblocking itself with error.cancelled. I believe that locks also get cancelled, and I'm guessing also await get cancelled. It's just that I'm not 1000% sure, so that's why I'm trying to use a slightly different example. So the parent was trying to read from the network, read fails, returns error.cancelled. Now the parent is processing its cleanup phase, right? It's returning with an error. So it's running all the deferrs and deferrs. So what it will do, assuming that everything was coded correctly, it will call, it will hit defer child.cancel, because normally when you start concurrent stuff, you always do defer task.cancel, right? So it calls cancel on the child. So now the child got canceled. And now the child, what is the child doing? Depends, right? If the child is computing Fibonacci, nothing happens. It will complete computing Fibonacci and then return to the parent, and the parent will then continue. The cancel will return, while the task.cancel will return, and then the parent will continue returning. But if the child is doing network, OS, whatever, sleep, whatever, then the child will be unblocked and return with an error, and, in turn. So that's how it works. And this whole scheme works. Basically works because, how can I say? You propagate cancellation in your code. Concurrent is synchronous. Concurrent is synchronous. No. Yes? I'm sorry. I don't know how to answer that question. So the call to the IO.current function is synchronous. Yes. But what IO.concurrent does is take its arguments, which are a function and some arguments for that function, and schedule them on another thread, assuming that we're using the IO.thread implementation. If we were using a different IO implementation, then the strategy would be not exactly what I just described, but conceptually the same thing. It just runs it on a different thing. Concurrent is parallel. My suggestion is this, Caritham. Don't use parallel that way. Here are the definitions that I would suggest. Parallelism is stuff happening physically at the same time, from the perspective of a human being. So a human being is observing two things happen in parallel. If doing thing A takes X time and doing thing A again takes X time, doing thing A in parallel with another thing A, or with another thing B, whatever, is in parallel if the total runtime is less than the sum of the two individual times. That's parallel. That's parallelism. Programs normally cannot observe parallelism. A program doesn't know almost anything about parallelism. The only thing a program can know about parallelism is if it has an estimate of how long a task takes, and it measures itself running that task to completion, or running like multiple copies of that task to completion, and thus it's able to conclude that there was parallelism going on. Otherwise, a program can only observe concurrency. And the fact that you can have concurrency without parallelism, the quintessential example is when you have a single core computer that can still do multi-threading. You can have a computer with just one core and that runs 100 threads. Those threads are concurrent, but they are never parallel because you have only one CPU. So the CPU runs one thread for a little bit, then stops, and then runs another one. And so if you're running the same task twice on a single threaded CPU, the total runtime will be at least the 2 times the time it takes to execute the task once. So that is a case where you have concurrency, but no parallelism. Normally, from a software perspective, you hope to exploit parallelism, but you don't control parallelism almost ever. What you do control is concurrency. Or rather, I guess you can control parallelism when it comes to SIMD. That is parallelism, not concurrency. Because you're doing the same operation multiple times and the time it takes is less. So SIMD is a form of parallelism that is not concurrency. But, when we stay in the realm of threads and async and await, that's concurrency. How is async distinct from concurrency? Concurrency. Concurrency. Let me see. Oh, I disconnected my drawing tablet. Well, it's mouse time. So the difference between asynchrony and concurrency is that asynchrony, let's say you have A and B, and A and B are tasks. What is a task? I guess that's also a nebulous definition, but let's say that they are 2 different functions. So let's say that a task for us is a function. It doesn't have to be necessarily that way, but for convenience, let's say that task A is just the act of calling function A, task B is just the action of calling function B. So these 2 things are asynchronous if they don't care about one another. For them to complete and be correct, one doesn't have to synchronize with the other in any shape or form. So for example, let's say that you have, for example, create table, I'm going to say CT, create table and then field table, in a database. Create table and field table, well, these 2 guys are not asynchronous. They have a synchronous relationship. They have a space synchronous relationship because we need to run create table, and only then you can fill the table. Because if you try to fill the table before the table has been created, then you get an error. That's the assumption, right? So this is like literally create table, and this one is insert. So these 2 things have an order relationship between them that has to be respected for correctness. But if you have, for example, save file A and save file B from my previous example, right, where these are like 2 files on disk and they have no relationship, you just need to save both at some point, then these 2 guys are asynchronous because you can do them in any order and it doesn't matter. So asynchrony is a property of 2 things that just do not care about one another. They are separate. Concurrency is the act of progressing multiple asynchronous things at once. So the idea is that we go back to having A and B. So concurrency is the ability to say, over time, I will do a little bit of A, and then I will switch. I will pause A, and then we'll do a little bit of B, and then I will switch back and do a little bit of A. And this covers all the possibilities. Like I do all of A, and then I do all of B. I do all of B, and then I do all of A. Or this mix A dash B slash B, B slash A, like the intermixed version. So this is concurrency. It's the ability to do that. What is it that gives you concurrency? Concurrency is threads. So for example, when you have multiple threads, those threads, for them to, they have to tend to do different things, right? For them to be able to progress, because if they are too intertwined, then it almost doesn't make sense to do threads. Sorry, I should add one other thing. Obviously, when I say that things are asynchronous if they don't care about one another, in the real world, this is always a property that is not complete. Like we always care about this being true. Like we care about partial asynchrony, because full asynchrony is like it's too extreme. It means that, well, let me put it this way: when you run a program and you call functions, at the very least, you care about completing those functions before you kill the process. So at the very least, you care about knowing that they are completed. So there is always some form of synchronization between the main function, the caller function, and these tasks, and maybe between one another. And there might be a little bit of synchrony necessary, but not a ton. So asynchrony, how can I say, it's not a binary thing where it's either all or nothing. In practice, you care about the degree of asynchrony. So you might have, for example, two functions that are very asynchronous, like they really don't care much about one another. So you schedule them on two different threads and you're happy. You might have two functions that can do some things, one independent from the other, but then they synchronize often enough that it's just not worth scheduling them on two different threads, because now you need to do atomic access to whatever state they share so much that it's just better to keep them on a single thread. So keep that in mind. It's not a matter of, this is not absolutes. But you can see that there is a clear distinction, right? A clear difference between save file A and save file B, and create table and fill table. So concurrency is the ability then to run these things a bit at a time. And so threads in a computer are a unit of concurrency. Threads are literally the thing that allows the CPU to run one function for a while, one task for a while, pause it by saving the state of the CPU in memory, load back into the CPU state for running the other task, the other function, run it for a while, and then switch back, and maybe switch also to something else. So threads are a mechanism for this. Sorry. This is my mouse calligraphy. So threads is one way of doing it. Green threads, and just do GT, that's another one. That's another way of doing concurrency. Green threads are basically, it's the same concept as threads. They're just userland, basically. So the idea of saving CPU state in memory and loading it as a way of switching task, it's literally the same thing, except that with threads, this work is done by the operating system, while this work here is done by you manually. If you watched me implement the why did it send me to Super HTML? Man, I trusted this thing. Why is this sending me to this tab as the first result when this is a match? Clearly a much better match. I need to change browser again. Anyway, so if you watch me implement operating system in 1,000 lines of code, that's what we were implementing here. We were implementing the OS implementation of task switching, and it's this bad boy here, context switch. It's like save state somewhere, load state from somewhere else, and then keep executing. It's this kind of stuff. So this is the kernel perspective, but then the green thread, the userland idea is roughly the same. You just have to deal with virtual memory in a different manner. What is another way of doing this? it's stackless coroutines. I'm gonna call them coro. Stackless coroutines, they are another way of pausing execution and doing something else. I showed yesterday how stackless coroutines work at a high level, so I'm not going to get into this again, but this is another way. So these are your concurrency primitives. Your parallelism primitives are, well, the things that offer you parallelism are SIMD, are CPU cores, mainly CPU cores, but also this was also a point that came up in a discussion with King a while ago. Hard drives are another source of parallelism because they can do DMA. So like you can basically tell, the CPU can tell the hard drive, write this stuff to disk, like write this memory to disk, or fill this memory with bytes from disk. And then the drive goes and does it. And the CPU can go do something else in the meantime. So that is another way in which you get parallelism. So asynchrony is kind of an abstract property. It's a logical property of the computation, right? While concurrency is a bunch of mechanisms that are not about abstract properties of the algorithm. They are like properties of the implementation. The implementation allows the system, one way or another, to write down up to what point the execution got to, do something else, and then return. So I hope that this describes what these things are. And I promise you that if you start being precise with how you use these terms, you will get a clearer picture in your mind when you start getting confused. Asynchrony is about order of events to the observer, which would be quantic. Asynchrony is about order of events. More importantly, is about lack of importance of the order of events, right? If you look at the Greek words, chronos is time. I think sin means same, so it's like same time, and is negation, so it's like absence of same time. Like synchrony is when things happen at, well, I think so. This came out also in a funny discussion with Andrew in the core team, where in English apparently people say synchronous to mean at the same time, but synchrony is not stuff happening at the same time necessarily. It's about stuff happening in a precise order, right? Stuff in, when something is in perfect synchrony, it doesn't mean that it's happening exactly at the same time necessarily. It means that it's happening in the correct order for the mechanism to keep working. So like, I don't know, like you have a bunch of gears and they need to, I guess they need to turn at the same time, but you don't want the teeth to be like this, right? You want the teeth to be like this in a gear. That's part of what makes the whole thing work. I don't know, sorry, that's the best example ever. In any case, this is synchrony. Asynchrony is when that's not necessary. So I think this is the best example. Save file A, save file B versus create table and field table. Keep in mind, in this case, these two things require order. In this case, these two things don't require order, but you do still care about maybe having both of them complete before you do a third thing, which could be calling exit on the process, for example. So this is the idea. And when your tasks are asynchronous, that's when you have potentially the ability to gain performance if you can run them concurrently. Because if you run them concurrently and below you there is hardware that can give you parallelism, then you get performance. This stuff is not only for performance. You might want to get also other properties from the system, but you know, performance is a big one. And so yeah, okay, I don't know. Hopefully that made at least some sense. I'm happy to answer questions if anything was confusing or, too confusing. What the heck is WSA? Status, mutex, init error. Initialize WSA. WSA startup. Oh, I think I know what this is. I don't remember precisely. Is this... I think this is some kind of Windows thing that you have to turn on if you want to have networking. Oh, yeah. C is not ready. Jesus. Yeah, Windows Socket API, right. I forgot. Wow, delightful. Okay, let's start from the beginning. When we init this stuff, let's see. Init and init single-threaded must be thread safe. Oh, GPA must be thread safe. So Borg is getting async again. Yeah. We're finally getting back into Borg. Oh, sorry, I didn't read this message. Let's see. They describe a different intent. With concurrency, you're expressing the need for two things to happen simultaneously. Wrong. Or rather... Oh, right. No, yeah. That's a good... Okay, that's fine. Sorry. I got overexcited. Yeah, the thing is, I think we need better terminology than happen simultaneously, because happen simultaneously might mean that you need parallelism, but you never need parallelism. So if you mean happen simultaneously, as in you need their execution history to overlap in time. So you know how I said, A, first all of A is fine, and then all of B is fine, then all of B is fine, and then all of A is fine, and then also some, weird mix is also fine. And where the weird mix is one of those things where you start with A and then you do some B and then you go back to some A and whatnot. Here's the thing. Sometimes A and B will have a synchronization point in the middle of the execution. And so for you to be able to reach that point, or rather for you to be able to have them complete and not deadlock forever, they both need to reach that point not at the same time in the sense of parallelism, but they need to reach that point while the other one has made some progress. So the point is that sometimes these two cases, A and first all of A and then all of B, or all of B and then all of A, sometimes these are a problem. They don't work. And the reason this can be, whenever one has inside a lock waiting for the other. And so you need some of these. And when you need, so you need for them to progress a little bit each. And in this case, you need concurrency. So in that sense, absolutely yes. You need concurrency for them to complete successfully. And that's what IO concurrent gives you. Yeah. If A and B share a lock, then both must be concurrent. Yeah. They must be concurrent one to respect to the other, in the sense that you don't have necessarily to call concurrent on both of them. You can call concurrent on the first one, and then async on the second. But that is based on how we define specifically IO.concurrent and IO.async. But yeah, they need to be running on two separate threads. So if we want to be concrete with what we are doing right now with IO.threaded, they must be running on two different threads. Because if you try to run them on the same thread, as in you run one and then you hope to run the second one once the first one has completed, the first one will never complete, and so you'll never get to the second one. So they have to be scheduled on two different threads. Yes. Okay, stack size, CPU count, concurrent count. Oh, wait, we did have concurrent count. Interesting. Oh, right, this is for the oversubscribing stuff. You shouldn't even need async on the second one. I would consider concurrent a more resource-hungry function than async. So I think you should, if it works, if it is correct for you, you should always prefer async over concurrent. Because IO.async is infallible, while IO.concurrent The concurrent returns an error. It can also fail. So let me put it this way. Maybe there will be a point in the future where we refine these ideas a little bit more and we conclude that it is better to do concurrent on both things. But for now, I would argue. Let me try to think where I have like a good example of this. I would argue that for now you should do async on the second one. Okay, none of this code helps me with what I want to show. Okay, this is has been renamed to concurrent. So here you have server and client, the server and client example. Here I would say that you have to do concurrent on the server, but then you can do async on the client. That's fine. You can run it on the same scope without asyncing it. You can also do that. Yes, you can also do that. Yeah, you can totally do that for sure. That would also work. Yes, absolutely. Because that's what async can do, right? Under certain conditions. So if async can do that and it's still correct, then you can also just call it directly. So if in this case there was something else that we would want to do while the client server, whatever thing is happening, we want to do something else, then it makes sense to do io.async. But if there's nothing else for us to do, so basically if we have to block here waiting for this whole thing to complete, then we might as well just call start client directly. Absolutely. If a group of tasks share a lock, then all but one of those tasks must be concurrent. Yeah. And the idea is that because you want to put them on different threads, right? And the last one you can put on the main thread, maybe. So that works because everybody else goes on a different thread, and then the main thread you use for the last one. If you want to, if it makes sense. You don't have to, but you can. And the advantage is that using io.async, you don't have to handle the error. That's the idea. Okay. All signal IO, all signal pipe. So this stuff is, I think this stuff is all mostly okay. Maybe the semantics of some things will be different. I think that we should call CPU count. We should have CPU count and like concurrent limit, maybe something like this. Also, this one, interestingly, this is a use size. Concurrent count. Oh, it's because this is the thing, threads. There's a mutex, there's a condition. So I'm guessing this mutex is protecting all this state. Okay. Well, let's see what happens next. If CPU count. Oh, because thread CPU count can return null in case of failure. No. Oh, this is an error. Oh my god, look at this. This is an error if. Wow. You don't see those very often in the wild. What about the case of real-time applications where the main loop shouldn't be blocked? Calling async risks blocking the main thread, so there seems like async concurrent is the only option. Concurrent is the only option. Yeah, so I think the answer is, in practice, yes. More abstractly, async await doesn't give you any real-time guarantee. In a sense, async await is the polar opposite of real-time. It's about adding elasticity to your code if you think about it, right? It's the idea of, well, yeah, if you can run this stuff in parallel, otherwise it's fine to run it sequentially, depending on what the current state of the system is. And this is expected to change dynamically based on the nature of the workload. So like if it's a web server, depending on the number of connected clients, how heavy are the queries that are running, depending on how all these things end up intertwining, then you want to be able to say, I'll do this, but sequentially it will take me maybe more time, but still I won't return an error if I cannot spawn a dedicated thread for this. Or you might decide to not do this, right? You might decide to put a limit to the elasticity of your system, because obviously, infinite elasticity means that your web server, if incredibly overloaded, will just keep accumulating requests until you run out of memory and it explodes. Although, I guess you could even use that as the actual limit of your elasticity without exploding. So you could say, I keep accumulating tasks as long as I have free available memory, but then at some point I don't have memory anymore, and so I can't do it anymore, and that's where I stop. But even in this case, there are some real-time requirements, right, to think to keep in mind. So, point is, yes, real-world use cases tend to care about real-world time, so for sure. But async is not something about guaranteeing that. So, if you're doing something like real time, you should use concurrent. Although, actually, you know what? I take this back. This is wrong. I was right in my statement. No, you should not use concurrent. You know what you should use? You should use thread.spawn. You should spawn a thread. Because the problem with, if you have an I should be back now. Let's see. Okay. So sorry everybody. Big thread, big async tried to cancel me. So if you are doing something like a music application, don't use concurrent. Use thread.spawn. Why? Because if you're using a because io.threaded will spawn a new thread, but the green thread implementation will not spawn a new thread on demand when you call concurrent, because the unit of concurrency of the green thread implementation is the green thread, not the OS thread. So the green thread implementation will multiplex green threads on top of OS threads. So you call io.concurrent, you are guaranteed to get a new green thread, which is a data structure in memory, but that will still be multiplexed on different threads. So my recommendation is, if you're doing a real-time application where you need to have a dedicated thread, do thread.spawn. That's my recommendation. You can still do, I guess you could purposely opt into, you could say, well, but then alternatively, I could just use the io.threaded implementation, and then I know that concurrent will give me a new thread. Sure, you can do that. That works. But I would say you don't have to. There might be other parts of your application that would be, there will be other parts of your application that would actually probably benefit a lot by having the green thread implementation multiplex multiple things on a lower number of OS threads. But not all parts of your application. So the key parts that, the where you have the GUI thread, where you have the music playing thread, where you have, I don't know, some DOS engine thread, just manage them explicitly, and still give your chance the opportunity to enjoy all the other non-blocking IO implementations. So in conclusion, IO.async is not, and IO.concurrent, they're not a replacement for spawning threads. You will still want to do that when it's a good time to do that. Shinrad X. Love your content. I'm a recent Zig lover. Do you by any chance have your Helix theme and config public somewhere? My Helix theme is one dark, so it's even, I think it's bundled in, so you just set one dark. As for my config, I don't have anything weird. I just have the left sidebar empty. So I can show you my config, but you know, I don't have a copy of it anywhere. But it's literally this. So mouse on, no scroll off. I hate autocompletion in Helix, so I turned it off. And then in the gutter, I only have div. So I do keep the yellow line for things that have changed compared to the last commit. But that's it. So I don't know, if you find anything here interesting, feel free to copy it. But I don't have a lot of funky configuration. I wonder for a game engine if it would make sense to have two runtimes, one for heavy processing, physics calculations, and evented for loading assets from disks or network. Maybe it would make sense. Like the general concept of having task queues with different priorities. Sure. Anyway, so CPU count. See the threads. I'm curious as to why CPU count has been programmed to also keep around the CPU count error. That is interesting. In any case, threads ensure total capacity precise. So we ensure to have space for n-1 threads. Otherwise, we do nothing. So if this stays an error, we do nothing. Okay. Concurrent count. 0. Positive sig action. I think we don't care about this, at least for now. This has to deal with cancellation and stuff like that, and I think it's okay for us to ignore that now. In single threaded. Oh, failing allocator, no threads, CPU count 1, current count 0. Okay, and then the init. Join worker function IO. So function IO returns the table with everything in. I think the next thing that we would want to change, also, you know what I forgot to do? Is also this git checkout -b IO threaded no queue. Okay, so we switch to a branch before modifying anything. So what should we change here? I think basically what we need to look at next is how IO.async works. So here we have a special case for built-in single threaded, which I think we don't need to have because this should be the result of single threaded. Basically would mean that we want single threaded and pool size equals 1. When it comes to IO.async should be the same thing. There should be no difference. IO.concurrent behaves differently, would behave differently. But in this case, we should not behave differently. So I don't think we should have this. Then user data is a pointer to threaded. What is threaded? Oh, it's us. I'm dumb. It's us itself. Then CPU count. Oh, CPU count. And oh, this is interesting how Andrew coded this. So we save the error, and if we are in the error case, it's basically this error is kind of treated like an enum. I mean, that's like a union. That's which is what it is. It's the first time though that I see an error being like, stored around and cached on potentially multiple times, like used for control flow this way. Anyway. What? What is he doing? IO calls concurrent. Oh, I see. Because concurrent spawns a new thread, then he says, well, if we don't know anything about CPU count, so I'm guessing down here there's some logic about what to do based on CPU count. But if we don't know anything about CPU count, then we just YOLO try to start a new thread. And if that succeeds, awesome. And if that fails, then we run the function immediately. Okay, it's just surprising that we call concurrent instead of async. Although, no, it should not be surprising, but that's how you can implement it every single time, right? Even though from the user perspective, async seems to be like a subset of what concurrent can do. No, it's not a subset. I'm just dumb. It's less powerful. I don't know. Well, no. It can do something that concurrent cannot do, which is run immediately. In any case, that makes sense. Okay, so then GPA, context offset, result offset, async closure. Async is optional concurrent. Yeah. Yeah. So here we catch. Okay, so we try to heap allocate an async closure. If we fail, we run the thing immediately. If we succeeded, then we write in there everything that's needed to, we basically we store somewhere all the information necessary to run this thing to completion, grab the lock, compute thread capacity, ensure total capacity, precise, on error as usual. We undo what we did and then just run the thing immediately. Otherwise, we prepend there our thing. Why do we prepend instead of append? That's also, well, it's a linked list, so that's fine. Yeah, right, because this is the linked list. This is not the array list. If threads items len is lower than thread capacity, we spawn a new thread which runs the function worker. So initially, this is going to be true normally because we will want to start, we will want to increase our pool. This surprises me though, because doesn't this code spawn a new thread every time we try to async something? Because I believe that like we append to the queue, but since we have no concept of saying like this is not saying spawn a new thread if there isn't one ready, because there might very well be one ready right now. In any case, If spawning a new thread fails, if there are no threads, then we pop our own task from the run queue, unlock, free it, run the thing immediately, we bail out. If we fail to spawn the thread, but there are other threads, and we just unlock, we signal the condition, and we return a pointer cast of the async closure. Which I guess it's our any future. Okay, it's our future. Async closure, it's our future. Yeah. Well, it's our any future. If we succeed, we append the thread, unlock the mutex, signal. Have a nice day, Diablo, or evening, or whatever it is for you. Okay, so this is async. This is definitely not how we would want this to work based on my design. So we want this to be very different. Let's try to sketch this a little bit. So it would have to work like this. Is there an available thread? If so, just give the task to that thread. If not, oh my god, I can't type. If not, can we spawn a new thread? If yes, spawn it and give it work. If not, I guess we could like somehow indent this. I don't know. If not, run the task immediately. That's how it should be. Okay. So how do we make this work? There are two things that we need to work out. How do we know that there's an available thread? How do we atomically consume it as we check? How do we hand the task to it? Because we also need to hand the task to it. And handing the task to it implies doing this, implies creating a future and also doing the cleanup. So there is some work that we need to figure out. Is there a limit to the amount of threads? Yes. In practice, there's always one, because at some point, spawning a new one will fail. The OS will run out of resources. But on top of that, we do want to have limits that we can impose on the process when you configure the event loop. Yes. Does the IO implementation lock when creating threads? Well, the current implementation does have a lock. So the current implementation does have mutexes to guarantee stuff. Look, the idea is, it's nicer if you can, get away without having to use locks for things, I guess. But like, that's always a possibility. This is what was happening here. So yeah. Okay. So let's take a look at std.pool, right? What does thread pool have for us? A mutex and a condition. A rank queue. Wait a second. I've already seen this stuff. What is going on? So I guess IO thread was already mimicking the thread pool. So what operation do we have for the public interface? We have spawn Wuji. Spawn. Sorry, against the wait group. Spawn WGID, spawn. Wait and work. All right, wait and work. That's also cool. Nope. So I think that the thread pool is not what we want. I think that we need to make it ourselves. So we need to have our own scheme to make this work. Which might very well be something that we do based off locks. So we'll see. So is there an available thread? So here's how we could do, is there an available thread? First of all, let's do this. First of all, we definitely need to have a handle to ourselves. So then we say, I think we can do something along the lines of, let's have an atomic counter of threads that are available. And we try to pop from it, basically. So I think we should do a like an atomic increment or decrement, something like this. So something like const like busy threads. Let's do it like this. Let's see. Available threads is t dot semaphores. std thread semaphore. A semaphore is an unsigned integer that blocks the kernel thread if the number would become negative. Interesting. So we create a semaphore. Producer posts. Consumer waits. No, concurrent cannot be semaphore.down. Unfortunately, I think this is why a semaphore is not the right choice. Concurrent cannot block if there is no available thread. Concurrent needs to always spawn a new thread in case there isn't an available one, while async needs to do that differently, basically. Let's see, available threads. I mean, we need to do some kind of counting, right? For sure. So here's what I'm wondering. Would it make sense to have an atomic variable and then only lock in the case that the atomic variable doesn't do what we want. Let's see, what are our atomic operations? I don't remember all of them. So documentation to do. It's a compare exchange, I think, or something like that. It's an atomic read modifier, right? Let's see. To do the references a pointer and atomically modifies the value and returns the previous value. It must be a pointer, a bool, a float, an integer, an enum, or a packed struct. And then there's atomic order. Yeah. Does that work? So we could take the value, available threads, and we oh, they don't even have try down. Yeah, but you see, even if they did, at that point, I don't need the whole full semaphore. I would only need the counterpart, which I can implement myself. So I can have an atomic number, and I keep subtracting to it every time I want to. You know what? That sucks. Okay, you know what? Let's have a simple implementation based on locks. Easy. So that we don't have to worry about it. And I think we can copy some of this stuff. So because we can reason also about CPU count also ourselves. So is there an available thread? Well, this guy knows. If CPU count, if we are in single threaded mode or CPU count is set to 1, then the answer is always going to be no. I think I want to change this. So CPU count is not this anymore. It's a U size. Okay. So we do not do this. We say, actually in init, also we need to change init, right? In init, we do catch 0. To do no limit in case of error. Then we don't need to do this. We don't have threads anymore. We don't do this at all. Concurrency limit set to 0. Perfect. Okay. So we say if the dot CPU count if thread CPU count is 1, which is basically single threaded mode, then we know for sure that we can just run the thing and call it a day. Okay. And this is also the case in when F single threaded. Actually, in here, we were saying that init single threaded is a different one. It's a different init single threaded is right. Right. Do we assert that we are not in F single threaded in here? We should assert that. Since this is the wrong API, if we are in single threaded mode, I think we should assert. Here we go. Use any single threaded instead. Okay, if CPU count is 1, then just run the thing immediately. There's nothing else we can do. Then, otherwise, mutex lock. Oh, you know what? This is interesting, actually. If we have CPU count... if we're in F single threaded mode... Well, no, we could be in multi-threaded mode with CPU count set to 1. So we don't want to specify that. Okay, so we now mutex lock because now we need to look at the part of the state that can change. So CPU count we want to rename in pool size. Or you know what? No, let's give it. I called it pool size in my example, but I guess we can leave it as is. Okay. So otherwise, lock the mutex. But we need this. So here we have an array list of threads that we manage. Do we want that? You would need compare exchange. It's okay. I'm going the mutex route for now. So, do we keep an array list of threads? I think it's fine. So this is the number of active threads then that we have. Okay, that is fine. So then we lock this and then we say if, but actually these are existing threads. What we don't know is the number of free threads. It's the number of available threads, right? Which we also need to have. If available threads count is greater than 0, then we subtract. We subtract 1, and then somehow we schedule. Then we need to do this, which we don't know yet what that should look like. But that's the idea. Otherwise, there are no available threads count. Can we spawn a new one? Yeah, I'll get to that. Can we spawn a new one? Actually, that is a good point. Why did we not have... I guess we had unlock in different places. Why did we have unlock in different places instead of defer unlock? I don't know. Okay, can we spawn a new thread? If t.available, well, if t.threads.items.len is lower than CPU count, or CPU count is 0. So if we don't know what is our CPU count, so we leave it unbounded, or we're below that threshold, then we can spawn a new thread. So this is the spawn and give it work case. Otherwise, this is the run the task immediately case. There we go. So I think this is our general strategy. Man, there's so much error handling and undoing that would be necessary. I'm actually not even convinced that this is the best way of structuring it. Maybe it might even be better to look at things differently. But in any case. So how does it work? Are these numbers comp time known? They're not. Interesting. Okay. So I think this might be a case where we don't do the else, but we do return instead. Something like this. Because then we can move this stuff here. Oh, can we actually? Yeah, I think it might be a good idea. Maybe not the alloc though. We don't want to do the alloc too eagerly. This might need to be copy pasted a little bit. We'll see. Okay. Okay. So let's see. Mini block around that lock. Oh yeah, that might be it. That's probably why it wasn't just a deferred block. We were probably trying to release it earlier. I guess before any free. Okay. So give a task to the thing, otherwise spawn it and give it work. Otherwise run it immediately. Okay, I think the next thing, it's either we copy here the thread spawning code, which we could do. Which we could do. Which we could do. So T threads ensure total capacity precise. This doesn't matter actually in this case because we were just trying to do +1. So this is okay. This can be a try append later on. So where is this thread spawning code? This is the thread spawning code. There we go. So this becomes, no, this becomes this. So we do thread spawn if spawning the thread fails, well, if throwing the threads fails, in our case, this cannot be the case. We cannot rely on other workers doing it. So I think it's basically this. Spawn the thread. If it succeeds, awesome. If it fails, run the thing immediately. Append not awesome capacity, but it's try append. This is the problem with keeping a linked list of these threads. Sorry, an array list of these threads, which is what I don't like. I wish we could avoid having this linked list, but sorry, this array list. But for now, okay, let's do it. But we can't just try. We need to catch. So catch. What if this fails? Oh, you know what? Actually, we should probably do this. And then we should reserve the capacity beforehand. We should definitely do the allocation before we try to spawn a thread so that we don't spawn a thread for no reason. That said, I think this whole array list should probably go. Anyway, t.threads dot ensure unused capacity precise. Is this a thing? Ensure total capacity precise. Well, at least we have that one, I guess. So GPA, just ensure capacity. Oh, anyway, it's okay. GPA t.threads.items.len +1 catch. We just return it. Okay. So if this succeeds, then we spawn the thread and we append it. We're still missing the handoff. We don't know how to do the task handoff. So why would you want reallocation every time? That is a good point. No, you're right. Let's remove precise then. And just ensure total capacity. Yeah. So there are two cases, right? The case where we know what the CPU count is, and ideally, we will pre-allocate the entire list in init to this correct length, which I deleted from the init function, so I need to put it back. And then there's the case in which we do not know the CPU count because it's set to 0, which we expect that to be the case when there's an error in detecting that. Is there ensure capacity? There's no ensure capacity. There's only ensure total capacity. So so if we don't know this, then we need to do the +1 here before we do this. Or we could do add 1. I think add 1 is the what we want, right? Which is essentially the same idea. There you go. Okay. The point is, we just want to make sure that the allocation happens before we spawn the thread, so that we don't have to handle allocation failure after we spawn the thread. That said, I'm still not convinced that we need these list of threads. But anyway, for now we have it. Then, then we need to do the task handoff. So what we're missing now is how do we do task handoff, and how do we replenish available threads count? You need to remove last if errors. Where? Would be nice if I had line numbers, huh? But I don't. Slot will be leaking. You are right. There you go. Or we could do pop. Well, I think I prefer this one though. Yeah. Okay. Artist has a len field beyond slice. Does it? It has capacity. Why would it have another length field? You already have one in the slice. So, that said, it is true that I'm not using the public interface. Okay, so this is the idea. Now, we need to handle allocation of the async closure, which we haven't done yet. Oh, you know what? There's also, instead of having these else, look at what we can do. If CPU count is 1, or t.threads items.len is greater or equal t.cpu count, and t.available threads count 0. Oh, but checking these, oh, I see what the problem is. Checking these requires the lock. Okay, I'm thinking about something else now. What I'm thinking about now is that I would like to be able to avoid having to allocate these async closure and then only for them to discover that, oh no, we can't anymore use it, and then I need to free it unless strictly necessary. There will be error handling that I think makes that necessary. But I think that if we just do some checking, some early checking here by combining a few conditions, then we can realize that it's actually not possible for us to do anything about it. That said, we could just move this code into a function, and we just call the function in the right place. And we still don't know. We still do not know how to do the handoff. Because here's the problem: we could pass in this thing as a argument to the worker function, and that would work in this case. But what about this case where the thread is already spawned? So we need to make this work. We need this. We need to integrate with this. So this is doing a run queue pop first. We could keep the run queue. So if this is the case, then we could keep the run queue. Do we still have it or did we nuke it? Still have it. We could keep the run queue. We just need to do the extra bookkeeping of how many free threads there are. Yeah, we just need this guy to do the number bookkeeping. It has a nice lock, so it should not be a problem. Okay, so the handoff is gonna happen through that linked list, like before. Okay, so so this is the case where we allocate the task and we append it on the queue. I think we need a function for this. Actually, what were we calling them in here? Async closure. There you go. Like, actually, you know, whatever. Function allocate closure and AC dot context pointer then context. Okay. Any future. Okay. This one's context and the result, and also wants alignments, I guess. Oh man, this function is such n. The heck is n? Oh god, this function is such a pain in the ass to call. N is this. Oh. This is such a pain in the ass to call. But I guess the good news is that we can try this instead of doing catch. I guess. What is start? This guy. Jesus. Okay. So once these things, I'm starting to think that this idea was a pretty function is not a good idea. Result office is a U size. Hmm, I'm not sure. I feel like there's something is missing. Are we really not using a result in here anywhere? Oh, we're using when calling, okay. For computing n. Okay, maybe it's not that bad. Hello, Calder. Okay, let's see how this goes. Also, we need to return. We need to return this. Then, let's see. Available thread count greater than 0. Decrement it by 1. Give the task to that thread. Yes, so that's that is allocate closure. GPA and offset context alignment is start. Is CPU count read only? I mean, conceptually, yes. We don't touch it. But it's a field, so you know it's Zig, so you know how it is. But yeah, no, we don't touch it. So we allocate the closure, which I think relies on some other computation that we have not done yet. Or did I move everything above? I did move everything above. Okay. So allocate the closure, and then how do we append it? This is it. AC closure node. Oh, this is also interesting because AC closure node, that also means that we cannot pointer cast this. This needs to stay an async closure. No pointer cast. Is runtime unmodified in init? Yes. Okay. So return. Okay, this code path should be implemented correctly. So if there are available threads, we decrement that. We allocate a closure, we prepend it, and we return. If instead there are no limits to how many threads we can spawn, and there are no available threads, or we haven't reached our limit yet, then we create a slot for the thread. Oh, also this needs a catch, and the catch needs to do this. Needs to run everything immediately. So slot does that, and then we allocate the closure as well. And then here to undo, we also need to free the catch, the closure. Sorry. So gpa.free destroy AC. Okay, so we try to make space for the slot. Yes. AC, I allocate the closure. If that succeeds, if that fails, oh, also, we forgot this. Oh, you know what is making this miserable? Think about it. You know what is making this miserable? We're not returning an error. If we were able to return an error, we would be able to do RDefer for some of this stuff. Instead, look at me doing manual RDefer. Disgusting. Absolutely disgusting. In any case, it's fine for now. Not using unsure unused capacity. Well, it doesn't matter much though. Whatever. One thing, same as another. So, so we allocate the closure. If that fails, we undo the thread stuff. If that succeeds, we spawn the thread. If that fails, undo the thread stuff, undo the thing here. Unsure unused capacity, you will need to do the -1 everywhere. Oh yeah, you're right. Okay. I was trying to do it, but I couldn't find ensure unused capacity. Okay, so we do have that. GPA 1. Okay, thank you. So, no this. No this. Thank you. Better. Okay. So we did it. We need the task handoff though. The task handoff is this. Okay. There's also condition signal. Should probably put them both in the same thing, huh? Oh, what am I doing? Okay. This should do it, I think. The next thing that we need to do is ensure that the worker keeps the bookkeeping aligned. So we need to go in function worker, and we need to do it right. So in here, whenever we spawn a worker and whenever we just put a task on the run queue, we always decrement this. So the worker doesn't need to do any decrement, but it needs to do an increment once it's done running something. So in here, so this is concurrent stuff. I'm gonna remove because we're not is concurrent. We're gonna not care about that anymore. Oh, closure has a is concurrent property. Doesn't matter. No, we shouldn't have this. Delete this. Ignore it here. We don't care. What we care is that once we're done running it, we do t dot available threads plus equals 1. There you go. Join requested. Oh, it's this is for exiting, I guess. Okay, so this all seems fine. Now we need to take care of toggle bit. You speak Italian now, man? So this is good. Let's look at okay, we have to do two things. Function init. We need to do this. If wait, init cannot fail. Interesting. So I guess we do t.threads ensure total capacity t.cpu count catch do nothing, I guess. I'm doing fine, thank you. Yeah, it's been a while. I've been busy the last few weeks, so I haven't been doing anything. And yeah, now I'm back at it. We're merging the async stuff toggle, which is pretty cool. But we're still having discussions about how the event loop should work. And so I'm doing a implementation of the event loop based on just spawning threads. So this is like the easy one, which ironically is the one that currently has a design flow in the current implementation. So I'm trying to make a POC of one implementation based on my design, which, to be clear, my design is literally the most straightforward way and naive way in which you can implement this thing, I think, in order to fulfill all of the requirements that in like all the properties that it needs to guarantee. So I'm just doing this to do some basic work so that it's not others, so that not everything has to be done always by others. Okay. So spawn worker. Okay, so with this we should be fine. Now here's the funny thing. Well, now we need to implement concurrent, and concurrent has its own set of things, right, that we need to care about. But here is the funny thing. I think that concurrent should be easy, because concurrent is going to work this way. Okay, so if we are in single threaded mode, we return concurrency unavailable. Yeah. You know what? Maybe I approached this backwards. I should have started maybe with concurrent. No, not even that. I think there's like there is a core of logic that both concurrent and async share, but it's not one using the others. So here's how it works. Here's how we do it. If built-in single threaded, or actually, no, that's it. Single threaded, we return concurrency unavailable. Okay. Then we say, okay, let's write down the plan like we did before. If there's an available thread, use it. That's the idea. If not, spawn if there isn't an available thread, but async hasn't hit its target yet, then spawn it. Unfortunately, we cannot call async. This sucks because basically we want to replicate some of the logic in async, but we cannot literally call async because async will always bail out on errors by running the thing immediately, and we cannot do that. Concurrent is not allowed to run the thing immediately. So we'll have to, basically the correct refactoring would take some of the logic, move it into a third function that both async and concurrent call. But in any case, so if there is an available thread, use it. If not, if t.threads.items.len is lower than t.cpu count, spawn a new normal worker, basically. Or let's do it this way. We'll leave the if not implicitly. If there is an available thread, just use it. If we can still, if there isn't an available thread, but we can still spawn normal thread, then just spawn a normal thread. If we cannot spawn new normal threads because we have hit our normal limit, then spawn a temporary one. Then otherwise we spawn a new one-shot thread. And what I call a one-shot thread is a thread that doesn't run worker. It's going to be a thread that runs a different function. Maybe it just runs start, I guess. We'll have to think about it. Almost. There's a distinction to be made between us running a new thread that we plan to keep around versus one that we are going to shut down once it's done. One shot does not go in pool. No, that's the idea. Basically, if we go above the pool limit, we make a thread that just runs this task and then shuts off. Which it is a design choice that obviously can have some downsides. So the problem is this, we're doing a bunch of work to avoid having too many threads open forever. And if we don't put any limit to these things, which by the way, as a user, you can just put, also, right, I forgot one point. We do have a measure of concurrency limit, which we haven't, which we currently have not touched on at all. So something to think about. In any case, so there's another limit there, but the idea is that my end proc is 12. So the idea is we keep 12 threads around always as we increase our usage as we need them. But then if at some point we need, because of IO concurrent, we need to go over 12, then we do that only briefly. We don't stay above 12. That's the idea. And it comes with a bunch of downsides, upsides and downsides. It's a series of trade-offs, right? Because you could have a very unfortunate program that basically uses IO concurrent to spawn a new thread, run one task, shut off the thread, spawn the thread again, run one task, shut off the thread again. That is very unfortunate if that happens. And it could happen. So, but at the same time, then what do we do? Do we spawn threads forever? No, we can't. One thing that we could do, here's one improvement maybe that we could do, which is have the concept of we keep the thread around for like 1 second after it's done running. So it sleeps for 1 second. We know that there is a temporary thread that is still waiting around before shutting down. And then if in that case, then we know that it will be able to pick up a task. And then otherwise it shuts off. But I would say that's an improvement that can be made later. Okay, if there's an available thread, use it. So we need to do this. There's usually an idle timeout. Yeah, that's the idea. Something like that. I'm not going to implement this now, but I think that would probably make sense to smooth over the phenomenon that I described earlier. Yeah. Why is async named async, but concurrent is not named concur? You know what? That's a good point. I concur. I don't know, man. I don't make the rules. You know who makes the rules? This is of the whole story. This whole story. This is the funniest part. You know who makes the rules? It's Microsoft, and they don't exactly make the rules, but who came up with async and await? It's Microsoft. They came up with this terminology. They implemented it first in F# and C#, and everybody else copied everything of what they did verbatim. In our case, we copied the name. The semantics are different, though. So, I don't know. I just like shorter names. Yeah, that's fair. But I think it's fine for concurrent to be longer than async. You should use async unless you really need concurrent. So, doesn't async comes from Haskell? You know what? You might be right. There might be some other, like, even more previous work where they were using async in some Haskell package that did some of that. But I would say that maybe that's where they took inspiration from. The first earliest prototypes. But based on what I've seen, so you might, if you look into this and find conflicting evidence and find papers that say otherwise, then please do share, because I would be interested. But based on what I've seen, basically Microsoft made the first like serious implementation in F#, and then ported that to C#, and then that's where async await became a popular thing. And then and then everybody else copied that stuff. I also would imagine that the Haskell stuff was not exactly. I do remember seeing on Stack Overflow somebody mentioning some weirdo Haskell package that was doing something related. But anyway, we should make everything async so we don't need the wording, and then just use nasync, right? When it's sync. Your own sentence almost suggests that there is a better way to say nasync than nasync. I'm almost there. I just cannot make the last connection. If only there was a simpler way to say nasync. It's fine. We can use nasync. I was surprised when I learned that Microsoft was the spearhead. Yeah, it's insane. There's also papers. It's very interesting how everybody copied their stuff uncritically almost. Maybe I'm being too harsh. You know what? I'm definitely being too harsh. I'm guessing other languages did put some time into thinking how they want to design their own async await, but almost everybody pretty much landed on the same design. The only languages that did differently are, Rust has features that you need to poll to move forward. That's a difference, although not a difference in how you use syntactically async and await much, but it is a difference nevertheless. You have Go that uses the Go keyword, and they don't have futures. I guess they're not the only ones because you have Elixir. So you either have a family of concurrent control flow languages that do concurrent control flow based on something else like CSP, Actors, whatever. Let's call it CSP. So you have Elixir, you have Go. Or if it's async and await with futures, everybody uses async and await pretty much in the same way. Rust has manual futures, manual as in you have to poll them, but you put async on function signatures, you use await to await a future. Python, same as C#. Ruby does not have async and await, I believe. I think they have green threads. Does anybody actually know? Not sync. Oh, we call it an S. Nice. Okay. If there's an available thread, use it. So we need to lock. Oh shit, look at this allocation that was happening outside of the mutex. And in our case, this is not happening outside of the mutex. Wait, this was optimistically allocating in order to shorten the mutex window. This is interesting. What are we doing? If we do that, then we don't need allocate closure. So here we are, should we be optimistic? You know what? Maybe a little bit of optimism. Maybe it's not too bad. Maybe just a little bit of optimism isn't too bad. Why not? Okay, fuck it. Let's be optimistic. Okay, let's see how much I broke this thing. So okay. Okay, then we lock. Bend. Ensure capacity, catch. Destroy AC. Destroy AC. Actually, are we freeing with destroy AC in here? This is doing destroy result len. Free result len. AC.free. Oh shit. Never mind. So we had the yeah, we definitely bungled certain things, huh? What is result len? Result len is u size. Oh, so it's a result.len in here. Okay. So we keep the property of allocating ones outside of the lock. Oh, and now I understand the absence of defer. It's because... Wait, is it? Why is it that? Why is it like that? You know what? I need to take a look at the original briefly. Let's just do that on GitHub. So lib std io io threaded threaded. Okay, let's see. What are we doing in it? Sorry, in async. Oh shit. Yeah, man. That is kind of important, right? It's kind of important that we unlock the mutex before we run the function. It's kind of important, isn't it? That kind of explains why there is no defer. You know, it could be that Andrew sometimes maybe forgets some of the language that he wrote, but maybe sometimes there is a reason for his actions, huh? Maybe sometimes there is some. Probably want to unlock this thing before running the function inline. No, what do you mean? I love data races. They're delightful to watch. Also, you know, I live near Monza. We have a big racetrack, and sometimes I go watch the races. No, I don't. I am actually fairly annoyed at tourists flooding the streets whenever there's a Formula One thing happening in Monza. Okay, yeah, that explains it. Okay, run return null, run return the thing, run return null, run return null. Okay. Nice. How far deep did you adventure in, like, with regards to like southern Italy? Because I think that the more you go towards the south, the more interesting driving becomes in general. Oh, mostly around Venice. Okay, so you stayed in the easy part of Italy to run around with a motorbike. That's nice. Well, I don't know if Toggle, if you still are of an age where you run around in a motorbike, or if it's like past that time. But this area here is pretty nice. That's Südtirol. The police on the motorway was wild, though. I would wrap myself around a lamppost in less than a minute if I tried one today. Really? Oh, man. Wait, I never had my running around on a motorbike phase. So, you know what I did, though? I bought a skateboard. So after seeing Andrew and Mason fly around in skateboards when they came here the other day, well, a few weeks ago. So these are photos in my town. Well, not that one. They added. There you go. So that one, this one. So this is a skate park in my town. And so after seeing them doing these things, I mean, this is obviously very advanced. Yeah, I got one. And guess what? I already rolled my ankle once. But I need to learn it. Like, I know nothing about skateboarding, so I'm not used to it at all. I know how to go on rollerblades. I can ice skate, but I've never done skateboard whatsoever. And it's a weird, complicated machine. Actually, no, the machine is very simple. It's just, I don't know, counterintuitive. So I don't know. I need to get used to the basics. And I already hurt myself once. Immediately, actually. Like, it did not take much for me to roll my ankle. So yeah. I had an 1100cc when I was young. Now I need a 10cc sofa. Nice. Okay, so with this, we should have everything. So with this, async is implemented. We don't need allocate closure anymore. We can nuke it. So now concurrent. If there is an available thread, use it. So we need to lock. Then if is there a reason why it's future.await instead of IO.await future? No, you could implement it either way. So there's like nothing to gain. How can I say? There's like nothing that you like. There's nothing that prevents you from implementing it either way. The idea though is that IO already has a bunch of functions on it. Like when you do IO dot, there's already a bunch of stuff in there. And await is something that you can only do on a future. So yeah. Would we make IO.async better? You can async a bunch of different things, but you can only await futures. So, you know, shortens the list of things available under IO by one and puts it in the one place where you cannot await anything other than a future. I guess technically you could await a wait group. I take this back. But But in any case, it wouldn't be a wait. It would be, I don't know, IO.await wait group. So I think that future.await is superior, but for, you know, fairly superficial reasons. Where is future defined? User space varsity. Future is split into two parts. IO.future is the future struct. Well, it's a generic type because a future is all. Here's also another reason why this is better than this, because this would have to accept any type on top of that. Future is generic based on the result. But then, and this is like, it's generic, but is not dependent on the implementation. Future is only dependent on the result type. So you can have a future void, you can have a future int, a future, you know, whatever, a future foo. But internally, it has a pointer to a type erased piece of information, piece of data, which is any future. And in our case, in this implementation, our any future is the closure that contains all the information for running the function. So in a sense, future is split into parts: a public interface, which is implemented in IO.future, and a private part, which is heap allocated. Not necessarily heap allocated, because, you know, it's allocator allocated. So your allocator could grab the bytes from wherever, but there's a part of it that is split off into a separate chunk of memory, managed differently, and that one is implementation dependent. Okay, now we need to do the handoff. And this looks a lot like what we were doing in async. So it's literally this. Oh, look at this. Bytes and... Oh, this is now split because we return concurrency unavailable on error. Okay, so this... Actually, all of this goes up here before the lock. So CPU count, we don't do it that way. GPA is fine. Rest is fine. EC, we do the mem copy. We lock. If there's an available thread, use it. Perfect. And you know what? I think I'm going to copy also the comments above because I think they're good. I'll try to use it. And this is literally the same code. Well, no, almost. If CPU count is 0, or we have capacity, then do this. On failure, we don't run stuff. So we can literally catch return. Oh, you know what? I think here we can defer. Maybe here we can defer for real. I wonder if Ziggy is moving towards making core of the implementation non-generic with generic wrappers. Will array list share this fate? In Rust, for example, it is implemented around a type array's array list. SED back. I don't know. No, well, the way it would work is that in basically you would keep around information about, well, the generic interface would pass down as an argument to the type arrays implementation the byte size of each element. So the type arrays would deal in bytes and alignment as a runtime known value that is hard coded by the generic interface. Your advantage, if you do that, is that you will have multiple instances in your program of the generic interface, but ideally that's shallow. And then all the business logic won't get replicated. You will only have one instance, so you will have less code bloat. I don't know, maybe. Wait, Why am I doing this? Why am I doing this? I can just defer free that stuff. Just like I defer unlocking this stuff. And so I don't have to do this. Here I can just return an error. Here I just catch return the error. Here I don't need to do this. Oh, you know what? We actually don't want to return that. I think we want to return out of memory. Do we have documentation that says what we are supposed to return? Concurrent error. Or just concurrency unavailable. May occur due to temporary conditions such as resource exhaustion or the IO implementation not supporting concurrency. Okay, so never mind. That's the only error that we return. Sounds good. Does it need to free it in happy cases then? Do we? No. Only in defer. Wait, what am I missing? So we return an error in case that we are already over the limit. Otherwise, we spawn a one-shot thread, which is kind of like this. Let's see. So I see what the problem is now. The problem is we might want to keep track also of these threads. I don't know, for other reasons, maybe. Honestly, I would keep track of them not with an array list, though. I would think I would keep track of them through other means. For now, let's not do it. I mean, this is a POC, so, you know, or regardless, these are like tweaks that can be added later on. So we do thread.detach. I think, yeah, thread.detach. Release the application on the caller to call join. Yeah, fuck it. Detach it. Okay, we spawn it with this stack size, but we don't call worker. We call a different function. And the function is going to be one-shot worker. And on catch, let's see what this was doing. Pop from the run queue, mutex unlock, AC free. Oh, look, this was still trying to unlock the mutex before the free. But it's fine because we already do that. Okay, so catch, return, error concurrency unavailable. That's it. I would even put a comma here maybe, and then do it like this. There we go. Okay, but we don't do worker. We do one-shot worker. We're going to need to pass it other arguments. We're going to need to give it AC, I think. Okay. I'm confused between the difference of a closure and an async closure. Shit, this thing has so much more stuff that we probably don't even need, do we? I think we only care about the closure. Start node, cancel TID. Yeah, we only care about the closure. Okay. Okay, we don't... Do we lock anything in here? Run qpop first, unlock. I think the first thing that we do is run this thing. So we just run it. Run it to completion. And then... we need the bookkeeping, right? We need to track of how many of these extra threads we have. So we should do t dot one shot threads minus equals 1. Do we need to do also... Do we need to signal? No. Maybe? No, we need to signal only if there's somebody waiting on a condition. Is there somebody waiting on a condition? You know what? I'm actually not sure. Maybe we should. We'll see. Okay, one-shot worker literally just runs the function and then decrements one-shot threads. So here we don't do a full async closure. Oh, shit. Actually, wait. We might need to do an async closure. Oh, no, 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 no. No, I think I understand what's going on. I think we need to do an async closure no matter what. And then... how does closure start do? Does it expect to be inside of an async closure? It probably does expect to be inside of an async closure, doesn't it? Yeah, it wants to be inside of an async closure. Okay, never mind. Although it doesn't matter because we can still do this. And then we still allocate an async closure and concurrent, which we need to anyway. But then what we pass down is ac.closure. So we can do that. So this should work. Okay, what are we missing? We're missing, I think, that variable that I made up earlier. Available thread count, CPU count, concurrency limit, available thread count, one shot thread count. If we have not hit yet concurrency limit, spawn a new one shot thread. We add another one of these guys. And then one shot worker decrements it afterwards. Okay. Then I think we're not in a bad spot. CPU count is that. Concurrency limit is that. Okay. Although for concurrent, I would say that for concurrent, if we don't have clear CPU count, I think it's fine. Okay, I don't know. Let's see what horrible build compile errors we left in the code. All right, we nuked is concurrent, and we need to deal with that. Oh no. So we don't care about this concurrent. Man, okay, so this is better. There's a catch one. 681. Group async. Oh no, there's another async one. Shit. Group async. No. But it's async. Oh no. What is group async doing, man? Append to the. So it is. Well, we're talking about what group does or does not. Group is heap allocating a future. That said, I'm not sure how you can avoid that. Like you need to copy the arguments somewhere. There's just no way around that. Nah, there are ways around that. Well, okay. Thread capacity, ensure total capacity precise. Thread capacity unlock free. Plus concurrent count. Group state. Group state fetch add. Sync one pending monotonic. And then we unlock signal. Oh god. Well, you know what? Okay, let's leave the logic here as is. Maybe it's a little bit wonky, but we can look into it in the future because we're not going to use this now in any case. Oh, there's the concurrent counting. I don't know. No field name available threads. Concurrency limit is 0. Yeah. Accept type IO any future found error out of memory. Try aligned unlock. Oh shit. 466. Well, around here. Oh, there's a try. There's a try and a catch. There we go. Expected the arguments found 119. Holy shit. It worked. We did not deadlock. Does this count as first try? I'll say first try. Well, they should be benchmarked, I guess, and compared. And also, we need to understand what the heck is going on with groups. Take the win. I'll take the win. But yeah, this is it. So this is an implementation of IO threaded that does that correctly. I don't know. Maybe I left bugs here and there. So, you know, we just survived one trivial run. Doesn't mean much. But I wonder if concurrent works. I don't know. I find it annoying that this catch has a return on a new line. Might as well put curlies in there at that point. Yeah, I think this concurrency is actually nicely implemented, mostly because we can use error returns and defer. Oh, look at this. Okay, we say that we increase the count of one-shot threads, but what if we fail to spawn the thread? Well, we need to defer, defer. There we go. Yeah, we need to understand what to do with group async. Because I think the group async should behave like my async. But I just didn't bother fixing it because we're not using it. So that's probably the next thing to do. And then, I don't know, just push the branch and invite people to comment on the design. So yeah. Well, I think this might very well be it for me. It's 8:30. I have yet to have dinner. I might have a meeting in half an hour. I'm not sure. Should probably check on that. But yeah, I think this might be it. Also, first stream from Windows 11, so everything went mostly well. We did lose connection at some point. Is it Windows 11's fault? Maybe, maybe not. We'll never know. But yeah. So that's the idea. Long story short, I think I did this mainly to support the conversation. Any start menu ads yet? I mean, we already had those. I'll tell you that I'll tell you that this new start menu really sucks, and it's full of garbage. Like your Windows 10 apps, Edge, don't want it. Outlook, don't want it. Microsoft Store, don't want it. Settings, fine. Although it's the bad settings menu, so photos, Xbox, solitaire, and casual games. I only play games that allow me to gamble, so don't care about those games. Paint, fine. LinkedIn. Why is LinkedIn in my star menu? Microsoft. Anyway, more pins, more recommendations. I don't know, man. Can I have neither? Yeah. So, okay, this was it. If you're interested in seeing what will happen with this implementation, check out the discussion on Zulip because if anybody cares about this stuff, it will probably be there. So, thank you all. And let me see if there's anybody to raid. It doesn't seem that anybody's doing Zig, so actually, I can check more precisely. It's zsf.zulip.org. I posted a link earlier. This one. Okay. No Zig, so this is it for me. Thank you all. See you next time.